Hello, class. Welcome, everyone. Let me share the slides with you to start the lecture. Okay. So today we make a little jump in the sections. I usually start by going into structural induction. But I thought maybe actually recursively defined data structures. But I thought this time I would try it slightly differently and actually first talk about recursive algorithms and then basically generalize it to other recursively defined things, which is not an algorithm, but a data structure. And I thought this would be a better logic because basically I think that students are more familiar with recursive algorithms. They're more natural. You might have seen them. And also algorithms in general are perhaps easier than data structures for students. So let's start with this one because it's just more familiar. Okay. So this stuff is basically section 8.7. There is more things in later sections. You don't have to read them right now. I would focus on section 8.7 first. Okay. And maybe 8.10. Okay. Okay. Now what has happened now? Okay. Okay. I hope reading section on the syllabus different from the slides. That could be. First of all, you're responsible for all these sections anyway, for the whole chapter 8. I decided to go first into recursive algorithms and then into recursive data structures. So I will sort it out after the lecture so that you know exactly which one. Although when you, yeah, I mean, the title of the section will tell you, but I will disambiguate it on the syllabus after the lecture. Like linked list, yes, that's an example somebody on the chat said of a recursive data structure very much. And trees, another one. That will be our standard example, but there are many others. So you see that you can define all sorts of useful stuff using recursion. But let's start with recursive algorithms because we are more familiar with this, I think. Okay, so okay, so first of all, let me start by saying what we will be writing algorithms in something called pseudocode. Pseudocode is not an exact science. Your pseudocode might be different from my pseudocode. It's everything about basically we describe algorithms in a way that can be mapped into any programming language. So using assignments, using if, then, else constructions, perhaps using for and I equals 0 to n in a loop. We will basically not use any other language formats than I think the ones I just said. Although correct me when that's wrong in a few lectures from now. Okay, so the syntax is informal, and we just want you to distinguish between what is when you assign a variable some value versus you test. So try to be clear that you're testing if a equals 0 versus you assign 0 to a. And otherwise, you can use commas, you can use semicolons, you can say if condition, and then immediately the consequent or you can say if condition then consequent. These are all understandable by everyone, and you can use any of them. Okay, so this it should be complete enough so that it can be unambiguously translated into a code. Okay, now what's a recursive algorithm? Recursive algorithm is an algorithm that has two major parts. First of all, it specifies how to compute an output on some sort of small inputs. Okay, and what small is, we'll see by example. The smallest. This actually exactly corresponds to base case of induction. We need to argue by hand in an inductive proof why a certain thing, why a predicate holds for some initial cases. Exactly the same way in a recursive algorithm, we need to specify how to compute in some initial cases. And then for all inputs except for those initial cases, the algorithm will compute its output by a recursive call to itself, in other words, to another call of the same algorithm on inputs that are smaller. So in order to compute the value of a function at point x, I will first of all specify how to compute the value at, say, x equals 0, x equals 1, x equals 2. Perhaps these are my base cases. And then for all other x's higher, my code will define the value of f of x by a call to f on x prime, where x prime is smaller than x. And that is exactly parallel to how induction argues that some statement is true about, say, parameter k if we knew that it was true about earlier values, about, in a strong inductive case, all integers that are smaller than k, right? You will see these parallels very clearly. Let's go over an example. Here is the code for computing exponentiation recursively. The algorithm is called power, and it has two inputs, a and n. The a is some real number, okay, and n is a non-negative integer. So n could be 0, or it could be any positive integer. What we could define, of course, we should be able to compute powers, exponentiations for other exponents, but not this code. This code, its input restrictions are specified here. A is unrestricted, essentially any real, n non-negative integer. And the output must be an exponentiation. So this is a specification of what the code should do. Okay, these are the inputs, these are the outputs. Okay, and here is a very concise code. It's a recursive algorithm. On input an, first line, if n is 0, then just return 1. Why is that? Because a to the power 0 is 1 always, regardless of a, right? X to the 0 is always 1, regardless of x. Else, so if that line does not return, so if this condition is met, this is algorithm already returns the value and ends. If it didn't end, therefore, if this condition was not met, then we assign to value p an output of a recursive call to algorithm power at input the same base, a, but the exponent is decremented by 1. And once you perform this assignment, which basically generates a recursive call to power, whatever this value is, you return that value multiplied by a. Intuitively, why would that work? Think of a, okay, just any base a. Let's say n is 3. This line is skipped. This line is executed. So this triggers a call to power at a 3 minus 1, which is 2. Okay, so the code comes back here, but with a new variable 2. This is not executed. This is executed. This is a recursive call to power with new variable equal 1. So we jump here. This line will be skipped. This one will be executed, but now with a power 0. So this line will be, the next execution of power will trigger this. It will return 1. And then what happens on the return? This will return 1, and the next guy up will return 1 times a. This will be returned then to the next guy who called. If you draw these frames, you know, I'll draw these frames on a piece of paper and post them after the lecture. How, you know, to sort of see the trace of this algorithm. Okay, that might be useful, but I won't have time right now. I will just do this after the lecture and post it. Okay, how does this and maybe I should do this right now, actually. Okay, video document camera, and I think I should stop sharing the slides, or otherwise it all gets messed up completely. Or so the students told me last time, right? So here is the power algorithm. Power at an does this: if n equals 0, return 1. Else do p is power of a n minus 1, and then you return a times p. Okay, that's the code. All right. Okay, so let's look. P at a input 3. Okay, it's now the variable n is equal to 3. So this line is not executed. This one is. So what we'll just do, it will assign this to the p of a2. And then it will return whatever a times p is. But this is a recursive call. So this is another call to this algorithm, just with a new variable n equal 2. So here n is equal to 3, and here in this call n is equal to 2. So in this call, do we execute this line? No, this condition fails. N is 2, not equal to 0. Else, so p is in this. So in programming, these are called frames of a procedure call. It has local variables, and this call also has a local variable. It's okay. This might have the same name as this one. They don't interfere because this is another execution of the code, which is basically independent of this execution. Okay, so yes, so this guy will still have this variable p, and it will be equal to power algorithm at and n is 2. We run it on n minus 1, so therefore we must run it on 1. And then if this call returns with a value, we'll return a times p. Well, but this is a recursive call to the power algorithm now with variable n equal 1. So again, we don't run, this will fail because n equal 1, not 0. P will be the power algorithm at a 0 because it's n minus 1, n is 1, so this will be 0. And then we'll return a times p. Is it clear? Okay, cool. Okay, when we are done. All right. So this is the final recursive call. Now it's with n 0. It's final because we finally are happy with this condition. So we just return 1. And we don't care what this code does because this is not going to happen, right? If the condition is met, we return 1. So this thing will return basically 1 here, right? Okay, sorry about a nasty looking arrow, but I attempted to put, basically P will be equal to 1. I mean, P at A0 returns 1. So here is a 1. So here is A times 1, which is A. So this call will return P, the value of P at 1 will be equal to A. That's what it will return. And so this little guy is A. And therefore this thing will be A times A, which is A square. And that will be returned. So, so this call, the P at A2 will return A square. So this little p will be A square. So this thing will be A times A square, which is A cube. And that will be returned, right? So whoever called P at A3 is going to get back A cube. So they will be happy. Questions on this? Okay. I mean, I don't know how many students have seen recursive algorithms. You know, some of you have taken introductory programming, some of you might not have. Okay, well, I take it that this is all okay with you. So I'm going to go back to my slides. All right. So okay. So here's my little code. You just have seen it, how it executes for n equals 3. And now let's prove something about it. So what I will want to prove is, well, it worked for n equals 3, but I want to argue that it actually always works. So here's a theorem. For any integer, non-negative integer, right, which was the range of inputs that I claimed the algorithm works correctly on, the power algorithm with this input will return the correct exponentiation, a to the n. And here's the code in its glorious conciseness. Now, how can we prove such a thing? Okay, induction. This is nothing else that you know, hopefully now see that this is a predicate. It's a predicate on n. For every integer n, I'm claiming the truth of the following predicate. The predicate is the power with input a and n will return a to the n. There is a hidden, sorry about this, but you know, I cannot dot all the i's, but I will in speech. There is a hidden universal quantifier for all a, right? Because a is not explicitly instantiated here in this predicate, but implicitly, what's, you know, I should have said is that it's for all a. Okay, and now you have a predicate. And so we will argue that this predicate holds for all n. by induction, just like the other predicates we have seen last week. So base case, we have to do, our initial case is 0, right, of the smallest integer for which we have to claim. And so that will be the natural base case of induction. I mean, natural, the necessary base case of induction. So let's see if this predicate holds. What does power algorithm return for input A and n equals 0? Well, let's examine the code. On n equals 0, clearly this line of the code will kick in, and therefore the algorithm will return 1. And 1 happens to be a to the 0 for any a, right? And so I'm done with the base case. What has to happen in the inductive step? The same as always, which is that for all let's do inductive function parameter k. So for all k greater or equal to the initial value 0, I want to argue that if the predicate holds on point k, then it holds at point k plus 1. So if pk, then pk plus 1. What is pk? It says that the algorithm power at input ak returns a to the k. What is p at k plus 1? It is that algorithm power at input a and n equal k plus 1 returns a to the k plus 1. And now see that actually these things that I was doing on the piece of paper for n equal 3, n equal 2, n equal 1 can be done in general. I didn't need to instantiate this for any particular point. I could have done this abstractly, so to speak, where this frame is called k, the algorithm here will be k, and this one will be k plus 1. And the same logic for why, if this guy returns correctly, then so must this. This is exactly an inductive argument that we need to make, and we can make. And okay, so what is this inductive argument? So first of all, so let's look. Okay, what does an algorithm power at input A and n equal k plus 1 do? Okay, let's look. If n equal k plus 1, would this line ever, this condition would ever be true? No, because if k is greater or equal to 0, then k plus 1 is greater or equal to 1. So this condition is basically false at that call. This algorithm will never run this line. What will it do instead? It will assign to a variable p an output of the power algorithm on input A and n minus 1. But n was k plus 1 here. So n minus 1 is k. So the algorithm will assign to this variable k an output of the recursive call to the power algorithm with the same base a, and now the exponent decremented by 1. So therefore exponent k. And by inductive hypothesis, namely this hypothesis, right? This algorithm does return a to the k. And we're basically done, because now the rest of the code will do what? It will take whatever this p is and multiply it by a and return that. So the algorithm will return a times p, which is a times a to the k by inductive hypothesis, right? We knew that, which is a to the k plus 1, and that's it. So it is exactly what we did between each of these steps, but just generalized to a power k. Hold on a second. Oh, sorry about that. Just trying to reduce noise here. Questions on this argument? Yes. I am looking at the chat and I see that some people have not taken algorithm classes, so maybe they do see those of you see the induction recursion for the first time. It's fine. That's we don't assume that you know that you have seen this stuff before. Okay. Okay. Looks like hold on a second. Let me so does anybody have questions about this algorithm or not? I see some questions on chat. Okay, but I guess the students are just asking one another, which is great. Oh, somebody asks assignment, and okay, yes. So I try to distinguish assignment from condition. Okay, and notation for assignment that I will use here. I might, unfortunately, you know, I apologize if I'm not consistent at some point, but I'm trying to be, so that to distinguish assignment from condition. Okay. Okay. So let's say something else about this algorithm. That it performs n multiplications when it performs this exponentiation. It's a different claim. It's a claim about running time, not a claim about correctness, which we have already proven, but about efficiency. Okay, how would this go? Exactly the same way. Okay, so this is a predicate. Now a new predicate. You're proving that the algorithm will perform n multiplications in order to compute. Okay, again, induction is of course by induction on n. In the base case, algorithm just goes here and returns 1 straight away, so it performs no multiplications check, right? Because we're claiming that it performs n, and that's correct for n equals 0. In inductive step, if the predicate holds about k, in other words, if power with input k performs k multiplications, then the predicate holds at k plus 1. In other words, power at input k plus 1 performs k plus 1 multiplications. And we're just working with the blueprint, right? By an inductive hypothesis, the number of moles in this call was k. The number of multiplications performed to compute this. So therefore, now, if you're running this algorithm on k plus 1, you're skipping this line, we argued this before. This line was a call to power a with k plus 1 minus 1, which is k. Now, in this call, by inductive hypothesis, you performed k multiplications. And now the only computation you still need to do is this multiplication, which is 1 multiplication. So k was how many moles were performed by this call with n minus 1 here equal to k. And 1 was this one more. I add them and I get k plus 1 multiplications that are going to be used by this algorithm on input k plus 1 and end of the proof. Okay. Let's take it up a notch, and but before that, let's just do so basically let's do what I want to do is a fast exponentiation algorithm, an algorithm that will do much less multiplications than n in order to compute 2 to the n or a to the n. So just a reminder, when you have, this is true about exponentiation, right? So in order to compute b to x plus y, you can compute b to the x and b to the y, multiply them. Also, this is true about exponentiation, right? So successive exponentiations of this, right, done successively translate into an exponentiation to a product of exponents. So let's do this test. How much is this? Okay. It's this one. because it's 3 times k plus 1, so it's is this. Okay. Now what about this? 4 times 2 to the k. Which of these is it? Right. Yes, it's. Oh, I don't know what has happened. Yeah, this one, right? Because 4 is 2 to the 2, and so I use this formula. 2 to the 2 times 2 to the k is 2 to the k plus 2. Okay. I will use it now. Here is a fast power algorithm. Another recursive algorithm to compute exponentiations on exactly the same input, but a different algorithm, slightly more complex, but it will actually be faster. So base case is the same. For if I start with an exponent 0, I just return 1. Otherwise, I divide my exponent, perform integer division. The integer division n-div2 gives me half of n if n is even, or half of n minus 1 if n is odd. Then I run a recursive I call fast power recursively on this new exponent. So roughly half the original exponent. And then if n is even, then I take this value and I square it. And that's my answer. And if n is odd, then I square it and multiply one more a. Okay. I will not argue today why this algorithm is much faster. That will be an exercise. Why is it much faster than the previous one? And what exactly is its running time also? Okay. And you will see that it is much faster. Okay. But let's argue that it's correct. So here is the algorithm again. Trying to make it more concise to fit in, right? The base case, you have the exponent, right? But integer, so you take a floor of n divided by 2. Then you run recursively on that halved exponent here, and what you do with the result depends on whether n is even or odd. If it's even, you return p squared. If it's odd, you return this. All right. Let's argue that it is correct. This is my predicate, the same as before. And I will use strong induction. Now, why I will use strong induction? Think, okay, you know what? The object that you can immediately relate these recursive algorithms to are sequences, definitions of sequences, and definitions also of recursively defined functions. This code, let's think of the output of this algorithm at point n as an nth element of a sequence. This line defines the first element of the sequence, right, as 1. This line defines the nth element of the sequence, the output of power at n, by a recursive reference to the value of the sequence at n minus 1. This you can write as a sequence, and if you do, then you will be maybe moderately surprised that it is a sequence that you already know. That last week or 2 weeks ago, we were already defining these type of sequences. They were just geometric sequences defined by a recurrence relation. The recurrence relation is that the nth element of the sequence is just a times the n minus first element of the sequence. And that was nothing but a recurrence relation, very simple one, that happen to define a geometric series. And so, therefore, by the geometric series formula, you knew that this is true, that the nth element of the sequence is indeed a to the n. Because all I do is that the nth element is defined as a times the previous one. So of course, right? But of course, well, we argued this by induction. This is exactly the same proof, just cast as a proof about a recursive call, a recursive algorithm, rather than a recurrence relation. Okay. So now, what is happening here? It is a recurrence relation. Again, I define nth element in the sequence, but now I define it using a reference to an element whose index is twice smaller. So it's not the previous element anymore. It's an element whose index is roughly twice smaller. It's exactly twice smaller, half even is even, or it's a floor even is odd. We have seen that for these type of recurrence relations, we need to use strong induction, because the fact that the previous element satisfies something is basically not helpful, because my value of this recursive call will be at n will be defined in terms of the value at n over 2. So the fact that like something is true about this call at n minus 1 is just not helpful. But strong induction would work. The base case does not differ, right? It's n equals 0, and we've already seen this now 3 times that this is correct. All right. What are you showing in the inductive step? You're showing that for all indices k of this recursion who are non-negative, if it holds that the predicate is true about all indexes up to this one. In other words, and what is the predicate? That the fast power algorithm at input n equal j returns a to the j. And that is true for every index up to this one. If we assume that, then we will argue that the fast power algorithm at k plus 1 is correct. And now you can see why I use strong induction, right? Because whatever my value n is, it will be k plus 1 here. I need to argue that it's correct. Well, what will happen with the code? This does not run because k plus 1 is positive. So I jump here. D is half of k plus 1. It is some number that is floored. So some number that is much smaller. But it does fall in this range. So therefore, this recursive call will be subject to this assumption. And so I will be good. Okay. Let's see how this works here. Here is the repeat of what needs to be proven. Don't know what happened there. Okay. I'll go by cases. Case 1, k plus 1 is even. Why k plus 1? I need to argue this about k plus 1. What happens with this code when the input n is k plus 1? So I will go by cases. K plus 1 is even. That's the easy case, right? Because this will just mean that D is exactly half. Okay, it will be convenient for me to, if it's even, let's pick some value for it. So k plus 1 is even. So let it be 2m for some integer m. Therefore, when I do div of k plus 1 div 2, this is 2m div 2, so it's m. I could have used d right here straight away, but I believe it's the point is the D does get, the value that you would expect. So since D is in this range, M is in this range, it's non-negative, or otherwise this guy would be negative, and it's also smaller or equal to K. So inductive hypothesis kicks in. Therefore, this recursive call is going to return a to the m, right? D is m. So here I'm going to call f fast power at exponent m, and therefore so p is going to be a to the m. Now, what about this line? Is n even? Yes, n is k plus 1. We are taking the n even case. So the algorithm will return p square. So it's this output square. So it is by inductive hypothesis, a to the m is the output of fp for this m. So it's square. And now exponents accumulate multiplicatively. If I take a to some power and then to another one, these two powers get multiplied. So it's 2m, and 2m was k plus 1. So I'm done. Okay. Questions on this? Okay. What about k plus 1 is odd, right? So that's the other case. So here n is k plus 1. And if it's odd, then it's equal to 2m plus 1 for some integer m. And when I do, so this line will be skipped again, right? This line will assign d will be k plus 1 div 2. K plus 1 is 2m plus 1 div 2. The floor of this divided by 2 is m plus 1/2, but 1/2 is lost in the flooring, right? So I get m. So again, m is in the correct range, non-negative and smaller or equal to k, and therefore, by inductive assumption, this call will be compute correctly. So p is equal to a to the m. So if this recursive call is correct, then I can replace this by a to the m. But what does the call do? N k plus 1 is odd, so it will go here. So it will return a times the square of whatever this call returned. So it's a times, by inductive hypothesis, a to the m square. And now what has happened? A to m to 2 is a to 2m, but we have one more a. So this is a multiplication in the base, which means now we're adding exponents. There is an implicit exponent 1, and here's the exponent is 2m. So it's a to 2m plus 1. And again, that was my k plus 1. Okay? So that takes care of the other case, and we are done. And it's not surprising that you would argue this by case of n even versus n odd. The code behaves differently in an even case, behaves differently in an odd case, and the relation between these this exponent and n is also different for the n even and odd case, right? So it's a natural split. Think of an even first. It seems to be easier. You do exact half, so this line is easier. You're done? Good. The other case is not that different. It's not that harder. Okay. Here's a little so again an exercise will be look at the speed of that code. How many multiplications does it do? And how to bound this number of multiplications as some function of n. So Here's a funny thing that I would like to compute. Nested exponentiation. So I want to compute a to the power of 3 to the power of n plus 1. I want to have a small recursive code to do that. Question to you. What goes here? What is the base case? N is a non-negative integer, so the base case should be n equals 0. What this recursive algorithm should do is take care of the base case. A natural one is like n equals 0 has to be taken care, right? Because I cannot compute at 0 using a reference to code, using a recursive reference. So here I will have n equals 0. What will I have here? Let's see. The n equals 0 this is 1. So this is 3 to the 1, which is just 3. So I just return a to the 3. What do I return here? Then maybe work it out on a little piece of paper. It is if somebody said a, no, that will be a constant function. If I just return a in the recursive call, then the value would be a everywhere. P also not. It will also be constant function, right? Because the next value of the sequence defined by this code is the previous one. So that will actually define a constant sequence. P times a to the third. P times a to the third. So this is a to the 3 to the n times a to the third. No, that will be a to the 3n plus 3. And just returning either returning a or returning p will give you a constant function. Pa to the 3 to the n. So I want to use the recursive algorithm in some non-trivial way. So of course this thing could be, well, just compute this thing, okay? Just return a to the 3 to the n plus 1. It will be correct, but it will basically assume that I know how to compute these powers. These algorithms are are useful only if all the instructions here are simpler than this computation to begin with, right? So if they're basically elementary, if I just restrict yourself only to some multiplications, the only thing you can do is multiplication of something by something. It is P3, yes. So it is p to the third power. Okay, what? If this call is correct, so if superpower does return the correct value, what is the value at n minus 1? Well, it's at n minus 1, this will be 3 to the n. So it will be a to the 3 to the n. That's what p would be. And now we're cubing p. So it's p times p times p. So it's multiplication, okay? I write it as a cube, but it's just 2 multiplications, a times a times a, p times p times p. Okay, so I'm cubing it. what has happened? Because I'm successfully applying exponentiation, right? So this is equivalent to these exponents multiplying. So it's this. And now these are the exponents. In the exponent, I have an expression which is 3 to something times 3 to something. Just happens to be 1. So therefore, this is the same as 3 to the sum of these exponents, n plus 1. So it's correct. Okay. And for everybody who on the chat, basically, used here is a more complex expression. For example, another call, recursive call to this, well, maybe that is true. Maybe that works there. So I don't know so fast, but here is a very, very, concise code. Okay. Okay. Do we have time for another one? Well, not exactly. It's 2:51. But well, whoever still can listen. This is my last slide. I have a recursive algorithm to compute the power set of a set. And if you have to go, do go, but maybe you can listen to these few last minutes later on. I want to have a recursive algorithm that computes a power set. The input is a set. The output is supposed to be a power set. The base case is like the smallest set, an empty set. If the A here is an empty set, I will return a singleton, a set whose only element is an empty set. This is indeed a power set of an empty set. So in other words, the set of all subsets of an empty set. And what are all subsets of empty sets? Is an empty set. This set contains those subsets. In a recursive case, which is if A is not an empty set, well, if it's not an empty set, then we can choose an arbitrary element of it. And this assignment, choose some little a as an element of this set, can always be done if A is not an empty set. Define A prime as a set reduced by kicking out this little selected guy. Now run the algorithm recursively. Come up with all subsets of A prime by a recursive call to this algorithm. Intuitively, that's a sensible thing to do, because if we have to, let's say that our algorithm, our set has n elements. A has n elements. How many elements A prime has? One less, n minus 1. So a recursive call has a hope of not creating an infinite loop, because that call will in turn define by a call to the same algorithm at a set which is one element still, n minus 2, and so on. These recursive calls will always work with a set that is one element smaller than the previous one. Eventually, it will get to the empty set and return. What do we do with these subsets? We take them. Here's a set of all subsets of A prime. Note, all subsets of A prime are also subsets of A, because A prime is the subset of A. So all subsets of A prime are subsets of A, but not all subsets. What subsets are missing? It's subsets who contain the little selected guy who was kicked out. So let's form all these subsets as follows. This is subsets of all. This is a set of all subsets of A prime. So take all do a loop over all of them. And any subset S, any set S in this power set, which is any set which is a subset of A prime, add a little guy to it. And take, this is a new subset of A, not included in this set, so add it to that set. Increment set P with this set. Okay? And after you increment it, you added all of those, that's what you return. The claim is that this recursive code is correct, that it does, no matter what set you start with, and no matter how you execute it, you have freedom here. It's non-deterministic. Your choice of the select element that you're going to kick out and run the recursive procedure on the rest. No matter how you do it, it always works. And you can prove it by induction, following the same paradigm that we have said. That will be another exercise. Okay, and there is more in the book, and there's going to be more in discussions. But also, what this week we'll do is in some discussion sections we'll have a review of the material of the last 3 weeks. Okay, and I take questions. Sorry if I kept. Anyway, I went over. Tell me if you have questions.
Professor, just to confirm, for this week, are the readings 8.7 and then 8.10 to 8.12?
This week's reading, yeah, for today, it's 8.7 and I think 8.10. I will recheck and also estimate how much really I will do on Wednesday.
Okay, because on your website it says it's from 8.7 to 8.9. So just want to confirm which is this week's reading.
So we will do the rest on Wednesday. But okay, we'll have to see if I get both 8.8 and 8.9 on Wednesday. Okay. I'm not sure if I will cover both sections on Wednesday. Any other questions? Oh, would the stuff be on the test? No, the test is on previous weeks. So it's up to strong induction. And even though we are using induction here, we are using it on recursive algorithms, which is a new thing. And we are not, that's not on test 3. The tests always go by, basically it's the first 3 weeks. Now we're starting new material, even though we are reusing tons of stuff from previous parts. If I will post on Piazza when I exactly tell you the sections that we just covered and the sections which I'm planning to cover on Wednesday. As I said at the beginning of the class, the last sections like 8, 11, 12 I'm not really doing them right now. They're related, but you don't have to do them right now. They really extend the stuff. to focus on 8.7 and 8.10, I believe.
Okay, so this lecture today was 8.7 and 8.10?
It's 8.7 for sure. Let me check if I'm just looking at the book right now to confirm. Okay. Oh yes. Actually, yes, it's 8.10 and 8.11 for sure. Yes. Sorry. And 8.12, analyzing time complexity of recursive algorithms. That's what we did. It's a big term for what we did, just arguing that the number of multiplications is n in that algorithm. Yes, so it's exactly what I said at the beginning of the slide. Slide 1. Okay, and I'll post on Piazza when I post it on the this modification on the syllabus. All right, folks. I'll see you on Wednesday. I don't know if you saw that some people asked if they can get feedback from the homework exercises earlier. So I said, yes, submit them and we'll try to grade them earlier. I'm not sure that we will manage, but you at least have that option. We probably will, because I don't expect many people to do that, and therefore we'll be able to grade them fast. No, well, I don't think that it makes sense for me to post solutions before Wednesday. I really don't. I don't see why that is necessary. I mean, like, if you don't know, well, submit them and do other exercises in the book where you have the solutions. So ask at office hours. Oh, after, of course, yes. We always post solutions after the homework is due. Okay, everyone. I guess that's it for questions. So see you later. Bye, everyone.